Hello everyone, in this video we're going to look at the test review. Now you'll notice this says 1055, this is the same material we cover in 1050, so you don't need to worry about that. I'm just going to go through each of the questions, and as I go through them I'll try to I'll try to share some general principles. So in this first question we're asked to sketch a function that is even and name two ordered pairs on the graph. So first off, what does it mean for a function to be even? You may remember there are two definitions that we use. The more technical one is f of negative x equals f of x. What does that mean? That's another way of saying that it doesn't matter if the input is positive or negative, the answer is the same. Another way that we state this is that we say it has symmetry about the y-axis. So I can be as creative as I want here as long as it looks the same on the left and right. So I'm just going to put some points and just make sure they're the same on the left and right, and then just connect the dots. This isn't meant to be anything in particular other than symmetrical across the y-axis. And the question asks me to name 2 points, and so this is 2, -4. This is -2, -4. And notice that it doesn't matter if it's +2 or -2, the output is the same. As a reminder, an odd function is a function where f of -x equals -f of x, or we say it has symmetry about the origin. We'll talk a little bit more about that in a later question, but the main idea is that it's something if you rotate it 180 degrees about the origin. So here's just a random graph that I'm trying to make odd. Try to make it a little better. If I rotate it about the origin point, it lands on itself. All right, let's play with function notation. In number 2, we're asked to find the domain of h of x. Now, h of x is a square root function, and square roots are an operation that can only work on certain things. I can only square root non-negative real numbers. Now, when we're talking about domain, we're always going to focus on real numbers. Some of you may have dealt with the square root of -1 before. We're not going to deal with it at this point. So the domain of this is whatever keeps x minus 9 from being negative. Another way of saying that is it's greater than or equal to 0. Because if it's negative, it's less than 0. So we want to keep it greater than or equal to 0. This is a symbolic way of saying non-negative. Now, this is an inequality we can solve. We can just add the 9 to both sides, and I end up with x is greater than or equal to 9 as my domain. Now, in this class, we prefer interval notation, so I would write this as 9 to infinity. As a reminder, this bracket here means that endpoint is included. I'd use a parenthesis to say it's not included. All right. Now, j of x. J of x is a linear function. All we're doing is multiplying and subtracting, and there are no restrictions on those operations. So my domain here is any real number. We can represent that in a number of ways, but our main way is saying from -infinity to infinity. Essentially, we're saying there is no restriction on the domain here. Now, h of j of x is part C. Find h of j of x. What that means is I'm taking the formula for j of x and putting it in for all the x's in h. So in h, I see I have an x just right here. So h of 12x minus 4 is the square root of 12x minus 4. I'm going to put that in parentheses to show that all is replacing the x, minus 9. Now, I can simplify this. We know the parentheses here aren't really going to change anything. I just put them there to help remind us that all of this is replacing x. So if I go ahead and rewrite this, I end up with the square root of 12x minus 4 minus 9. Let me extend my square root symbol to make sure it's all under there. And so I end up with the square root of 12x minus 13. And then part D right here just has us do the reverse. I'm taking the formula for h of x and putting it in for all the x's in j of x. Well, h of x is the square root of x minus 9. And now we need to see if we can simplify. You may be tempted to try to bring the minus 4 into the square root or to multiply across the 12. Unfortunately, we can't do that because multiplication does not distribute over a square root symbol. This is, in fact, the best we can do here. And I guess I'll box out the final answer for the previous question. In the first question, let's look at 3. Write an equation for the graph of the parent function, square root of x, after it has been horizontally shifted 3 units to the right, stretched vertically by a factor of 6, and then shifted down vertically 7 units. So I'm just going to call this f of x, and I know I'm going to have a square root with an x in it, but I need to apply those transformations. So my first transformation is shifted 3 units to the right. You may remember that when we do things horizontally, we apply it directly to the x, and it's the opposite of what we expect. So 3 units to the right, it seems like a positive movement. We do the opposite, so it's a minus 3. We now need to stretch vertically by a factor of 6. That works exactly how we think it should because I'm just modifying the y values. So I multiply by a 6 out in front. Shifted down vertically 7 units is a minus 7. And that's our answer. Now let's look at inverse functions. So we have a quadratic function. Our instruction is we need to find a domain restriction that makes the function 1-to-1. Now you may wonder why. Well, let's draw a rough graph of this function. I'll draw it over here on the right. X plus 2 squared minus 5, that's moved left 2 and down 5. Once again, this is rough. It's not meant to be perfect. But it looks something like this, where I have a parabola. This fails our horizontal line test, meaning it's not invertible. So we're just going to take part of it. We can either take the right side or the left side. It doesn't matter. I tend to take the right side, and so we look at what gives us just the right side. Let's see, this vertex is at x equals -2. And so we're going to say our domain restriction is from -2 to infinity. So that's us just using the right-hand side of that parabola. This allows us to find an inverse. Now, I am going to show you two ways to find the inverse of this function. I'm going to give myself some more space to do that by going over here to the right. So we have k of x equals x plus 2 squared minus 5. And here's the first method for finding the inverse. This is sometimes considered our classic method, where we switch x and y. We make x the output of the function and y the input, and solve for y. Now, this is often used because it follows directly from the definition of an inverse. An inverse is where you switch inputs and outputs, where you do things backwards. So I can solve for y to get this function. And I can use my classic solving skills. I'll add 5 to both sides. So I end up with x plus 5 equals y plus 2 squared. And now we square root both sides. This is where our choice of side, if I'm using the right or the left side of the parabola, really matters. Since I'm using the right side, I'm going to take the positive square root. If I took the left side, I'd have to do the negative square root, because that's where each side comes from. The right side is where x plus 2 is positive. The left is where x plus 2 is negative. So I square root both sides. I end up with square root of x plus 5 equals y plus 2. I can subtract the 2 from both sides, and I end up with the square root of x plus 5 minus 2 equals y, which tells us that k inverse of x is the square root of x plus 5 minus 2. Now, the second method I'm going to show you for finding an inverse is quite similar in that it uses the same thinking, but there's a little bit of a trick thrown in. Now, I call this method the reverse operations reverse order method. Now, let me tell you what I mean by that. Think about taking apart or putting together a toaster. If I'm taking apart a toaster, often the first thing I'm going to do is unscrew or remove the outer shell. If I'm putting together a toaster, that's the first thing I do. So notice the methods for putting together and taking apart a toaster are opposite. You do opposite operations in opposite order. That's what an inverse function does. So if I look at the original k of x function and think about what is being done to the x according to order of operations. Well, the first thing is done is I add 2, because that's the thing that's right next to the x inside the parentheses. The next thing that happens is everything is squared. And then after that, the result of that squaring, I take the result of that squaring and subtract 5. Well, if I want to find the inverse, I can just think of it as I'm taking inverse operations in inverse order, reverse, opposite, whatever your favorite word is. So since I minused 5 at the end of k of x, for the inverse, the first thing I do is add 5. So notice reverse operation, reverse order. Since the thing I did right before adding 5 was squaring, in the inverse, I use the square root. And since the first thing in the original operation was adding 2, that's the last thing in the inverse. So it's a minus 2. So I'll write that all out. I have an x, I add 5 to it. I take the square root of all that and then subtract 2. And you'll notice that's exactly the same as what we got with the classic method. In fact, if you look at the algebraic steps I took in the first method, I first added 5 to both sides. I then square rooted both sides, and then subtracted 2. So this reverse operations reverse order method is, in a sense, us recognizing what will happen if I switch variables and solve. So either method is correct. Now, let's do another inverse function. In this one, we're asked determine if it has an inverse. Well, how do we know whether it has an inverse? Well, it has to be 1 to 1. We know our square root function. Let's see, this is a square root function that's moved left 2 and up 9. That means it's going to look something like this. It has this arrow that grows slowly. Notice it's 1 to 1 in that it passes the horizontal line test. Any horizontal line that goes through it can only go through it once. So we can find an inverse. So let's go ahead and find it. I'm going to go ahead and use my inverse order inverse operations method just because I like it. So let's see, the first thing that's done is I add 2. The second thing that's done is a square root. Third thing that's done is an add 9. So in the inverse, the first thing is the opposite of the last thing. So I have a minus 9 first. And then I take whatever I have and square it, because that's the opposite of the square root. And then I minus 2. So G inverse is x minus 9, all squared, minus 2. Now I need to find the domain and range of G inverse. Let's first talk about the domain of G inverse. Our initial thought is that since quadratics have a domain of all real numbers, this must have a domain of all real numbers. However, the important point is that it's the domain of an inverse. Something we need to remember is the domain of the inverse is the range of the original. And that makes sense. We're switching x and y values. So if I look at x plus the square root of x plus 2 plus 9, my original function, we know this plus 9 at the end is what gives us the range. We know square roots grow upward from that plus 9. So the range here is from 9 to infinity. And then we can either we can do something similar for the range of G inverse. We can either find the domain of the original, or we can look at G inverse and recognize that squared functions, quadratic functions, only go upward from that minus 2 on the end. So my range is from negative 2 to infinity. All right, moving on. So we're going to use the graph to figure out where the function is increasing. A big thing to remember with these questions is we always answer in x values, and we always read left to right. So as I'm looking left to right, I want to look for where this is increasing. So as I look left to right, this is increasing right here, because that's where it's going up, but then it switches and starts going down, and then it increases over here. Now, once again, I use the x values of the changes to write this. So let's see, the first bit, assuming the graph goes on forever, it goes from negative infinity up to the x value of 0. because that's the x value of my first big green dot, union, because there's more than one piece that's increasing, and then 2 to infinity. I always use parentheses with increasing and decreasing because it's not increasing or decreasing at the turnaround point, it's turning around. Now, if I look for where this is decreasing, that's when it's going downhill, looking left to right. And that's this chunk right here. And that's the x values from 0 to 2. Now, let's talk about a relative minimum. A relative minimum is where a point is lower than the stuff around it. It doesn't mean it's the smallest point ever. It's just the smallest in its area. It's kind of like being the shortest in your class versus the shortest in the world. So this point right here at 2, 0 is a relative minimum. And then this other green dot where we switch from increasing to decreasing is a relative maximum. Is this 1 to 1? No. How can we tell? If I try to do the horizontal line test, there's lots of places where it fails the horizontal line test. There are multiple times a y value is used for different x values. All right, moving right along. We're now going to do a transformation. We have x squared is our parent function, and we move it right 3. We reflect it over the x-axis and move it down 4. So let's write a formula. So if I move it right 3, remember horizontal changes are the opposite of what we expect. So I'm going to put a minus 3 here. And then the basic function is squared. Reflecting it over the x-axis is a vertical reflection, a top to bottom reflection. So I put a negative outside the squaring. And then finally I move down 4, so I have a minus 4 out here. Since this is quadratic, the domain has to be negative infinity to infinity. This is just a basic quadratic. It's not coming from anywhere strange, so we can just say its domain is all real numbers. And as we mentioned before, this number at the end is an endpoint of the range, but this function is going down because of the negative in front. So that negative 4, instead of being a bottom endpoint, is a top endpoint. So I go from negative infinity up to negative 4. The y-intercept is where the function equals 0. So I can just put 0 into the function. And if I calculate that all out, I get negative 13. So my y-intercept is at 0, negative 13. The real zeros are where the function equals 0. So I'm going to have to try to solve negative x minus 3 squared minus 4 equals 0. Now, some of you may notice right away that this is impossible. A negative square of something is going to be negative or 0, and then subtracting 4, a negative minus 4 is going to be even more negative. It doesn't seem like this can get to 0. Let's verify that. I'll add 4 to both sides. I have negative x minus 3 squared equals 4. I'll multiply both sides by negative 1 to get rid of that negative in front. And I get x minus 3 squared equals negative 4, which is impossible. That has no real answer. So we have no real zeros because I'm trying to square something and get a negative. I'll sketch the graph to help reflect this. I moved right 3 and down 4. And since it's a negative quadratic, it opens down. Wasn't that fun? Let's return again to odd and even functions. You may remember that we had kind of a trick for remembering even functions. If something's a polynomial, if it's just x to powers, a function is even if it has all even powers. That's why it's called an even function. Something is odd if it has all odd powers. Now let's look at the function given. It doesn't matter that there's a 3 in front of the x to the fourth. All that matters is that we have an even power here. So I have an even power, but what's the power on x? Well, we can think of it as an x to the first, and so that is an odd power. So I have a mix of even and odd powers. What does that mean? This is neither, because of that mix of even and odd powers. For number 10, we're undoing a composition. I want to find two functions where I can think of 10 as being their composition. Remember, this g is an inside function. So what functions can I see being on the inside here? You may see many different ones. The classics ones are thinking of that 2x plus 3 as the inside. And then f of x is everything outside that. I'm taking that input, cubing it, and then taking the square root. Alternatively, I could say that the 2x plus 3 cubed is the inside function. That's g of x. And so the outside function would just be the square root. Both are correct. The idea is just finding an inside and an outside. Now we're going to use composition to verify an inverse. So how do we do that? Well, we need to show that when I compose the two functions together, I just get x. Now, technically, I need to check both ways. So I'll start with f of f inverse. That's taking the formula for f inverse and putting it in for x over here. So f of f inverse of x, in this case, is 2 quantity cubed root of x minus 7 over 2 plus 3 minus 3 cubed plus 7. And let's see what happens. The first thing I notice is that this plus 3 and minus 3 zero out. And I'm left with 2 times the cubed root of x minus 2 over 2 cubed. Excuse me, I've been writing a minus 2 and it's supposed to be a minus 7 up there. We know that a cube root is something that's actually designed to undo a cubic power. So those two invert each other, they undo each other, just leaving us 2 times x minus 7 over 2 plus 7. Those 2's divide out. They make a 1 multiplied on, so I have x minus 7 plus 7, which equals x. All right, I'll now do it the other way. I'll do f inverse of f of x. So the cube root function is now on the inside. I'm going to replace its x with the cubic function. 2 times x minus 3 cubed plus 7 minus 7 over 2 plus 3. I notice right away that that 7 and negative 7 zero out. So I have the cubed root of 2 times x minus 3 cubed over 2 plus 3. These 2's divide out. So I get the cube root of x minus 3 cubed plus 3. That cube root undoes the cube. So I get x minus 3 plus 3, which equals x. So since I got an x in both directions, I have confirmed those are inverses. I have to do both for a full confirmation. All right, now we're going to look at piecewise functions. A piecewise function is a function where the formula changes depending on the input. It's kind of like parking in a paid parking area. You end up paying different amounts depending on how long you're there. In this case, it's a more abstract formula where we look at different formulas for different inputs. So let's start with f of negative 4. The input, well, that's an input that is less than or equal to negative 3. So that's the formula I use. Well, that just equals 7. That's a constant function. So no matter what, if it's less than negative 3, the output is just 7. Let me zoom in a little bit. Now, negative 2, that doesn't fit the first inequality, but negative 2 is in between negative 3 and 9. So I'm going to use the second formula. So this equals absolute value of negative 2, which is just 2. Similarly, 0 is in between negative 3 and 9, so I put 0 into the second formula. The absolute value of 0 is 0. Now, for our last one, use this nice green here. We know that 16 is greater than 9. So I've used the third formula, the square root function. So the square root of 16 is just 4. And that's it for piecewise functions. Now, let's look at the domain of kind of a crazy function. We have two major issues here. Let's deal with them one at a time. So my first issue is a square root. You may remember from before that we need this numerator, we need the stuff inside the square root to always be greater than or equal to 0. Well, this one's not too bad. I can subtract 9 from both sides. And I get that I need x to be greater than or equal to negative 9. Now let's talk about the denominator. What does the denominator contribute here? Well, we can't divide by 0. So we need to find the place where this denominator equals 0 and cut it out. So I know I need to solve for when x minus 2 equals 0, and that's just when x equals 2. So we need both of these things to be true. We need to use x values that are greater than or equal to negative 9, and we specifically have to skip over 2. Now, this is an appropriate way to write the domain, but the instructions say write your answer as an interval. So let's translate that and statement into an interval. Well, first, we know my lower bound is -9, and I can use any number from -9 until I get to 2, and I use a parenthesis to show that's not included. I use a union sign to show I'm going to have to write another interval, and I go from 2 to infinity. So these parentheses show that I am skipping 2. I can do anything right next to 2. I can do 1.99, 2.003, but I have to skip 2 itself. All right. Let's do one more composition problem where we're going to do different types of combinations. This one here, at first asks us to find f plus g of x. The reason we write it here is to emphasize that when we add two functions, we still get a function. So for f plus g of x, that's just going to equal f of x plus g of x. Then I just get to simplify, which is x squared plus 2x plus 4. I can also multiply two functions and get a function. So for this one, I need to multiply the two functions I'm given. Now, one thing that helps me with these functions is when I multiply them, one way I do it is kind of like how you do the multiplication algorithm in grade school. So this helps me remember I do the -1 times the 5 to get a -5, the -1 times an x squared, put an negative x squared there. Then I have to do 2x times 5 in the second row, which is a 10x, and 2x times x squared is 2x cubed. If I put that all together, that gives me 2x cubed minus x squared plus 10x minus 5. I'll go ahead and put a nice box around that, show it's my final answer. Now, the f open circle of g of x is a composition. This is where I put g inside of f of x. So notice I'm putting g of x inside the formula for f. Now I'm going to use the formula for g of x and put it in there. 2 times x squared plus 5 minus 1. As I go through and simplify that, I get 2x squared plus 10 minus 1, which is 2x squared plus 9. And that's my final answer. Last but not least, I get to do the reverse, where I take the formula for g and replace all of the x's with f of x. So I'll go ahead and put that formula in. 2x minus 1 squared plus 5. I'm going to go ahead and use an area model to help me multiply 2x minus 1 by itself. It's one of my favorite ways to multiply polynomials. It helps keep me from going crazy. I get 4x squared minus 2x plus 1. So this is the same as 4x squared minus 4x, so just combining those negative 2x's, plus 1 plus 5, which in the end is 4x squared minus 4x plus 6. Well, wasn't that fun? All right, one last question where we're going to graph an inverse. We have to sketch an inverse of the function given. And that's this red function here. The big thing to remember is an inverse is where we switch x and y. So if I can figure out what those marked points on my original are, I can use those to get the inverse. So on the original, it looks like I go through the point 5, 2, the point 6, 3, the point 9, 4, the point 14, 5, and the point 21, 6. So that means in my inverse, if I switch x and y in those points, they'll be on the inverse. So my inverse has the points 2, 5, 3, 6, 4, 9, 5, 14, and 6, 21. So I'm going to go ahead and plot those points. 2, 5, 3, 6, 4, 9, 5, 14, 6, 21. Just connect the dots. Whoops, that was not my best line. And now I have drawn the inverse function. All right, that's it for this review. Thank you for watching.